Hi, I'm Drew,
I'm Austin.
and this is our final project for CSE 545. So, just to give you a little bit of background and introduction to start off with, for our problem that we chose to solve for the project, we decided to go with the bin packing problem from that list of NP complete problems. The bin packing problem can be described as a classic optimization problem. The primary objective of this problem is to effectively pack a set of items of various sizes into a minimal number of bins or containers, each bin having a fixed capacity. So the reason we chose this problem is because we figured that not only could we complete it in a reasonable time frame that we were given, and it would also integrate the genetic algorithm and the wisdom of the crowds. But it also has somewhat of a practical use in solving this problem because if you think in everyday life, this is pretty relevant. For example, packing stuff for moving apartments or something like that. But overall, the goal with our problem in mind is to reduce that number of bins by using an incorporated GA and WOC combination type algorithm and then represent those results via dynamic GUI GUI that we will show later on.
So with our approach, we used Python as our language of choice, which is what we've both been using all semester. I'm most familiar with. We implemented the random, tkinter, and time libraries. Um, for the random library, we generated a set of random numbers within constraints set by the number of entities and the range of numbers used as our data set for packing. The tkinter library we use to generate data representation on a GUI, and the time library we use to mark and start the end time for to calculate functional execution time. Um, the genetic algorithm, or the GA, serves as the core of the program. It's responsible for orchestrating the GA through crossover, mutation, and selection mechanisms. Using a wisdom of crowds strategy, it incorporates the best performing individuals from each generation to guide subsequent populations in aim for the most optimal solution. At the end, a GUI called bin packing GUI, which is a window that we titled, then visually represents the best solution through that process by illustrating allocation of items into bins with optimized representation. The program begins with asking the user to define the quantity of items and maximum item size. Using those parameters, it generates random items and proceeds to solve the bin packing with the GA. First, it initializes space by storing items sizes and bin capacities. Then it takes the previously defined parameters to generate a random set of items. The initialize population function allocates those items, and the GA function then runs multiple generations of allocation and comparatively searches and defines the best performance based on the wisdom of crowds approach for a specified number of generations. Finally, the results are displayed on a newly formed window with visual bins with items inside efficiently sorted throughout the algorithm. The user is then prompted to click a print results button to print a list of the best solution, number of bins, and execution time without including idle time, where the user defines parameters and views results. The user can see a new window appear after closing the bins window and after clicking that print results button that shows a line graph representing the best fitness value on an improvement curve.
All right, now that we've talked about our approach to the problem, I'd like to talk about some of our results that we got from our testing. So as you can see here on the screen, here are parameters, at least some of them that we chose. We've got bin capacity, population size, generations, bin width, bin height, item width, item height, and scaling factor. And fine tuning these was vital to conducting the experiments for this problem and on the code. So as you can see below, we also decided to keep certain parameters constant. We did this so that way we could focus on fine tuning specific parameters that we'll mention in the next slide. And for our actual testing, we did sample runs, but we also made sure during these sample runs to use the same value for varying number of items and maximum value. Again, these set values will all be shown in the next slide. So moving on, here are the parameters that we used for each of our test runs and experiments. For run 1, we did 10 items and maximum item size of 10 as well. Those will always stay the same. The bin capacity was set to 30, population size set to 50, and generations set to 100. Now, the results of this test will be shown in the next slide where I have images and such. The other run, we did 20 items and 20 max size. We used the same bin capacity, same population size, and generations. We just changed the max items. Later, just to show, we also did a experimental run where we left the bin size the same, used the same parameters as run 1 and 2, but up the population size and generations to 200 and set those as the same to kind of see how that would affect our outcome. So I'll move on to the next slide where each test can be shown here. And as you can see from these examples, each time you run the code, it's going to show what you, the user, input for the number of items and the item sizes. Once you input that, this window will pop up that shows the bin packing solution visually. And if you want the rest of this information printed, you'll just use the print results button. And then it will give you the best solution, which corresponds with what's on the screen in the GUI. It'll give you the number of bins used, which you obviously want to minimize, and then the runtime for that specific run. As you can see, it varied based on what parameters were set and so on. And then once you got all this information, you can close out this bin packing window. And just for an example, this is what the genetic algorithm improvement curve would look like. And later on, when I show the code demo, you'll see what this looks like in real time.
So discussion with our results, keeping the number of items and maximum value is important for obtaining accurate results. For finding the best solution, not only does the execution time change, but tuning parameters affects this too. The program does a decent enough job reducing the number of containers for optimization like shown in the results. However, as the number of items increase and the bin capacity remains the same, the program struggles to reduce the number of bins. Manually changing this can help, but for this experiment, it would be better to keep the number the same. Like you saw in the previous example of the improvement curve, a smaller data set with a lower quantity and generations in our runs shows a flatter curve, but with a larger generation population like displayed here, we can see a more drastic curve. In this example, our population size was 1,875 through 43 generations with our number of items and maximum value set to 56. As the population size increases and the generations increase, the fitness value along a curve will decrease as the algorithm runs until it about remains constant as it finds an optimal solution. The average runtime for our tests rounded to 5 decimal points was 0.07063 seconds, or around 70.63 milliseconds. The greater the population and quantity of our generation specified, the longer the runtime was. Thus, our big O notation for runtime would be O to the n-gm, where O times n-gm, where n is the population size, g is the number of generations, and m is the complexity of the operations within each generation. An example, evaluating fitness, crossover, and mutation. In order to get optimal runtimes, a smaller set of parameters will always benefit runtime. The most important parameter in that regard would be the number of generations. More generations means more run-throughs and repetition, so careful consideration of that is number one when prioritizing runtime.
Okay, now that we've got that discussion out of the way, I'd now like to show a demo of our code live. So as you can see here in my Visual Studio, I've got the code open, and just for testing's sake, I've got the bin capacity parameter set at 30, population size parameter set at 50, and generation set to 100. All the other factors that I remain constant, just like earlier. So I'll go ahead and run this. As you can see, it starts off by asking the number of items. For testing's sake, let's do 34. Make sure whenever you run this, keep it the same, or else the values will be skewed and you'll have duplicate items. So once you hit enter and you run it, it does go a little bit off screen, but as you can see, it's visually represented. Now, once you hit this print results button, it'll give you the actual data. So that way, if it does go off screen, you can still see what the best solution is. And it'll give you the total number of bins used as well, along with the runtime. So you've got all that information now. Once you've got it, you use this button to get it. You can go ahead and close out the bin packing solution window, and then the improvement curve will show up. You can go ahead and analyze this, kind of use the zoom function here to check out what various numbers were. You see it kind of started out at 23, then it goes down, it hits at 22 for a little bit, and then it goes out. And once it finds that optimal solution, it'll kind of remain at that for the rest of the time. Really just kind of stays at 21 until it's gone through all the data, as you can see here by the total. It gets really constant once it finds that optimal solution.
In the future, we could experiment with different algorithms entirely, or improve our current GA with wisdom of crowds implementation further. Exploring the use of larger problem instances or more specific tasks could help our program possibly be more applicable for certain challenges. And following that point, using real world data could help boost our program's practicality and usefulness, as well as give us more to learn and work with.
So, in conclusion, our main takeaways are that in our project, we successfully implemented a genetic algorithm and wisdom of crowd approach to solving the bin packing NP complete problem that we set out to solve. As discussed prior, it's also very important when it comes to parameter selection for this problem, especially when you want to fine tune it or run specific tests or experiments like we did in our case for this project. If you wanted to test different parameters or get different results, you could always change around a few of the constant parameters that we set to get more data and test the algorithms more. We also know that the algorithms, it can always vary, and we did take this into account when testing. We did this by trying to limit the amount of randomness when experimenting by selecting only certain parameters to test on and then setting others constant, like we showed before.
If you have any questions, you can contact our school emails as displayed on the screen. And with that, thank you.
Thank you very much.